Hey there. The periodic table, it's not just some static chart on a classroom wall. It's actually packed with stories. And today, we're going to dive into a really dramatic one. It's all about a quest, a story of three neighboring element families and their search for the ultimate prize, stability. And it all kicks off with one simple question.
So what is it that makes some elements, super reactive, like fluorine, which will basically react with anything it touches, while others, like neon, are total recluses? They just want to be left alone. Well, the answer boils down to one single powerful motivation.
And that motivation, it comes from these little guys, valence electrons. Think of them as the electrons on the very edge of an atom, its outermost shell. They're the real main characters in our story today. The number of these valence electrons, well, that defines an element's whole personality and kicks off its quest for that perfect, stable setup.
Okay, so to really get this quest, we've got to start at the finish line. We need to meet the ones who've already won the game. So let's begin with what I like to call the stable elite, the elements over in Group 18.
And here they are, the noble gases. You can basically think of them as the Zen masters of the periodic table. They are just perfectly content, chemically inert, totally unbothered by all the drama happening with the other elements. You could say they've reached a kind of chemical enlightenment.
So what's their secret? How did they get so zen? Well, they've achieved the ultimate goal, a completely full outer shell of electrons. For the chemists out there, that's the ns2np6 configuration. What that really means is they have 8 valence electrons, and 8, that's the magic number. That's the stability that all our other elements are desperately trying to get to.
And this incredible stability, it has some really fascinating consequences in the real world. Because these atoms are so happy on their own, they don't bother forming bonds with anyone else. They just float around as single, monoatomic gases. And they've got such a tight grip on their electrons, it's almost impossible to steal one away. And gain another one? Nah, they have zero desire for that.
Want a crazy example of just how weak the forces between them are? Just look at helium. Its boiling point is a mind-boggling 4.2 Kelvin. That's just 4 degrees above absolute zero. It is literally the lowest boiling point of any substance we know of. And why? All because its atoms are so stable and content, they have practically zero reason to hang out with each other.
Now you'd probably think these aloof Zen master elements are super rare, right? But nope, they are hiding in plain sight. In fact, the third most abundant gas in the air you're breathing right now is argon, a noble gas. Yeah, almost 1% of every single breath you take is made up of this perfectly stable, chemically inert element. Wild, isn't it?
All right, so we've met the stable elite. Now let's meet their next-door neighbors. These are the elements that are so agonizingly close to reaching that perfect state. Let's dive into the high-stakes world of Group 17.
Say hello to the halogens. And look, if the noble gases are the Zen masters, then the halogens, they're the most aggressive collectors on the block. Their entire chemical identity, their whole personality, is driven by this one desperate need, to find just one more electron.
And here's the reason why they're so aggressive. It's all about their electron configuration, Ns squared np5. That means they have 7 valence electrons. 7! They are so close, they can practically taste that perfect, stable shell of 8. And that's what makes them unbelievably reactive. They'll do pretty much anything to snatch that one missing piece of their puzzle.
Now, even though this desperate quest for an electron unites the whole family, as you go down the group, you see this really beautiful, clear trend in what they look like. They shift from a yellow gas like fluorine to a greenish yellow gas like chlorine, then to a red liquid bromine, and finally all the way down to the violet solid iodine. It's just a fantastic progression.
But you know how it is in families, right? The firstborn is always a little different. Well, in the halogen family, saying fluorine is a little different is a massive understatement. This element doesn't just follow the trends, it completely shatters them. So what is it that makes fluorine such an outlier? For starters, it's tiny, exceptionally small, and it has the highest electronegativity of any element on the entire table. It is the undisputed champion of pulling electrons towards itself. But here's the paradox. The bond it forms with another fluorine atom is surprisingly weak. And it's this unique, weird combination that makes it so exceptionally, and sometimes dangerously, reactive.
Okay, let's move one door down from the halogens to meet the final family in our story today. These elements are also super reactive, but they have a slightly different problem. They have two spots to fill in their outer shell, which actually gives them more options to find that stability. So let's meet the versatile partners of group 16.
These guys are called the chalcogens, and that name, it literally means ore formers, which is perfect, right? Because so many of the metals we find in the Earth's crust are bonded to these elements. Think oxygen and oxides, or sulfur and sulfites. They are absolute masters at building partnerships.
So what's their challenge? They're working with an ns² NP4 configuration. In plain English, that means they have 6 valence electrons, putting them too short of that noble gas perfection. This gives them options. They can try to grab 2 electrons from another atom, or they can form 2 separate bonds. This makes them way more chemically versatile than the single-minded halogens next door.
And this leads to a really interesting energy puzzle. You'd normally expect it to get harder and harder to remove an electron as you move from left to right across the table. But group 16 actually lets go of an electron more easily than its neighbor, group 15. So what's going on? Well, it turns out group 15 has this surprisingly stable, half-filled p orbital thing going on. So for a group 16 element, losing just one electron actually gets it to that more stable state. It's a trade it's more than happy to make.
And hey, just like we saw with fluorine, the firstborn of this family also plays by its own set of rules. The oxygen that we all know and depend on to live is completely different from its heavier siblings like sulfur and selenium.
I mean, for one thing, while the rest of its heavier family members are solids, oxygen is a gas. It's also paramagnetic, which is a cool way of saying it's weakly attracted to magnets. But maybe most important of all, its compound with hydrogen, H2O, water, is a liquid. The hydrides of all its siblings, they're nasty toxic gases. So yeah, these unique properties of oxygen are, quite literally, what makes all life as we know it possible.
Okay, so we've seen the quest, right? This desperate search for a full outer shell of electrons. So now let's get to the payoff. What actually happens when these elements succeed? What do they end up creating?
This whole quest for stability has a huge, massive impact on our world. Let's take sulfur from group 16. Its chemistry is the foundation of something called the contact process. This is how we produce sulfuric acid, which is one of the most important industrial chemicals on the entire planet. We use it to make everything from fertilizers and detergents to paints and pigments.
And we see the same kind of thing when the halogens from group 17 partner up with hydrogen. They all form acids, but the strength of that acid depends entirely on how weakly the halogen is holding on to that hydrogen. So tiny fluorine forms a really strong bond, making hydrofluoric acid relatively weak. But as you go down the group to big old iodine, that bond gets much, much weaker, making hydroiodic acid a really strong acid.
So when you think about it, the huge, vast difference between a totally inert gas, an aggressive salt former, and the oxygen that gives us life, it all comes down to a quest for just 1 or 2 electrons. It's pretty amazing. And it really makes you wonder, doesn't it? What other incredible stories are hiding in the rows and columns of the periodic table?